Welcome to the course on computer design of electrical machine. We'll have a lecture 17 today on design of single phase induction machine part 2. So with the outline of presentation, we'll like to talk about standards on single phase induction motor, then design consideration, specification, constructional features, then design equation, performance calculation of single phase induction motor, and exercise and numerical problems and references. So coming to standard on of single phase induction motor, which normally followed in the design. So single phase induction motor are extensively used for domestic, office and agriculture applications, just fan, mixer, refrigerator, washing machine, machine tools application. And the single phase induction motor have poor power factor and efficiency compared to their three phase counterparts. Apart from the standard mentioned already, three phase induction motor dedicated to standard single phase induction motor are IEEE 114/1982, that is IEEE standard for procedure for test procedure for single phase induction motor, and IEEE again modification of it, IEEE 114/2001, IEEE standard test procedure for single phase induction motor. And again this standard is further modified typically in 2010. Another standard IEEE 839/1986, IEEE guide on procedure for testing single phase induction motor and full phase induction motor for use in hermetic compressor. Then NEMA SEM S1 2000 standard for small electric motor, and NEMA MG 11 1977 with modification of typically in 97, 2001, 2007, 2012 for energy management guide for selection of and use of single phase motors. And then ANSA and NEMA MG 1 2016 motors and generator. So now coming to the design consideration and specification. Now coming to design consideration, single phase motors are built in fractional horsepower rating, majority of them, leaving exception apart for some are of higher rating. So design of such a small rating motors need a special attention. So major design consideration of single phase induction motor are like typically pull out torque or maximum torque, then starting per unit torque, starting per unit current, then power factor, pull out power factor, then rated efficiency, and then the capacitor value for starting and running. Depends on type of which discussed last time, and operation at different voltage and cooling aspect. Well, single phase induction motors have several specifications required by the motor designer. The type of motor, because there are plenty of type of single phase induction motor which we discussed last time. Then rated power, starting torque, rated speed, number of poles, rated frequency, rated voltage, power factor, slip, full load, and thermal rating. Now coming to constructional features of the single phase induction motor, as you can see in the photograph, we have normally squirrel cage rotor, then wound field stator, along with the typically the other accessories, typically the capacitors, maybe depends on starting or running, as you can see in the photograph, like, and of course the shaft, like. The rotor consists of laminations punched together with slots, and the slots appear as tunnels when the rotor is assembled. So tunnels are filled with the aluminum poured in molten state, which we call die casting process. In some motors, the copper bars and copper end rings are used, formally being bridged into the latter, and the rotor slots are screwed to achieve a quieter operation and to avoid some of the physical phenomena like cogging and crawling. Now you can see the typically number of your rotor with the aluminum die casting. You can clearly see how the screwing is there on the rotor slot, and then of course on the right side you can just see the aluminum die casted or aluminum bars rotors, like, which normally used for high efficiency motors because the copper have a less resistivity compared to the aluminum. So now coming to the switches and capacitors, these switches are used to cut the auxiliary winding out of the circuit when the motor has attained 75% of the synchronous speed, and these switches are centrifugally operated whenever is possible, so they have magnetically operated. And AC electrolyte capacitors are usually mounted outside the body of the motor for starting, and of course another capacitor for running, that we call it running capacitors, and of course responsible for power factor correction also. Then you can see as in figure that you have a two capacitor. One capacitor AC electrolytic is for starting, with cut by centrifugal switch, and other capacitor remain in the winding for high rating motors, so that it runs as a perfectly very close to perfectly two-phase balanced motor with the phase shifting capacitor in the auxiliary winding. I mean, there are many concepts that whether you should have a two currents at quadrature to create the two-phase field in this motor, which really give a rotating magnetic field as far as possible to very close to the balance operation. Now coming to design equations of single phase induction motor. So in order to estimate the main dimension of a stator, the output equation relating to volume of active material, speed and rating is to be derived. So let the phi is the flux per pole, B average is the magnetic specific magnetic loading, K is the winding factor, AC is a specific electric loading in ampere turn, and F is the frequency, and S is the synchronous speed in RPS, and T is the number of turns of main winding. Beta is the efficiency at full load, cos phi is a full load power factor, and P is number of poles, V is the rated voltage, and tau is the pole pitch, and I the full load current in main winding. The output power in terms of kVA we can call it VI into 10 power minus 3, and where V is 4.44 kW F by Tm, where phi is B average pi d L by P, and F is NS P by 2. So using these equations, we can say V will be equal to 4.44 kW NSP by 2 B average pi dl by P into Tm, and if you put in this equation in the kVA, it will be 4.44 kW NS P by 2 B average pi dl by P Tm I into 10 power minus 3. As we can say, AC specific electric loading can be 2 Tm I upon pi d, or Tm I is AC pi d by 2, then kVA will be 4.44 kW NSP by 2 P average pi dl upon P AC pi d by 2 into 10 power minus 3, where we can now say kVA, we can of course further simplify this equation. It comes 1.11 pi square kW B average AC into D square LNS into 10 power minus 3, or kVA as the output equation we can say Q equal to C0 D I square LNS, where D is the diameter at air gap, and L is the stack length, and S is the synchronous speed in typically in RPS, and C is the output coefficient. So we can say this kVA input to the motor is equal to Q C0 D square I LNS, where the output coefficient C0 is 1.11 pi square kW B average AC into 10 power minus 3, and for the rating of the machine in horsepower, this Q can be calculated from that HP into 0.746 convert into typically into kilowatt divided by efficiency and power factor eta and cos phi. So this gives the kVA rating of the machine, which we can put in this output equation and get the typical value of the main dimension, the one relation between the main dimension D and L. So output equation can be DI square L equal to HP 1046 divided by eta into cos phi into C0 NS. The range of efficiency varies from 20% for 20 watt air pole motor to 70% for a 750 watt motor, and power factor ranges for 0.54 split phase and 0.99 for permanent capacitor in induction motor. So now you can see the rating versus full load efficiency versus power factor. So if we talk about starting from 40 watt to 1 kilowatt, you will find the efficiency varying from 38% to 75% and power factor 0.45 to 0.7, and the value C eta cos phi for calculation of DL may be also directly read from this table. So we have a watts RPS and C0 eta cos phi, I mean starting from 3.6, which comes C0 cos phi 0.9, and if it goes for high rating, typically watts per RPS 18, so this also goes to like 18. Now coming to the choice of specific loading, we have two specific loading like average plug density, which normally varies between 0.35 Tesla to 0.55 Tesla, and the usual specific electric loading varies from 5000 to 15,000 ampere per meter. So now D square L product is obtained from the output equation. The variable D and L are obtained from the aspect ratio, varies from 0.6 to 3 depending upon the diameter size available in standard stamping, that is lambda equal to L P by pi d I, and typical value of aspect ratio here for different poles. I mean typically it varies from, if you go to from 2 pole, it varies from 0.6 to 1, and if you go to 8 pole, then it from 2 to 3. So 2 pi is the number of poles, that is we represent normally capital P. So now coming to ratio of inner diameter to the of the stator Di with the outer diameter, based on empirical method for variable pole pair is shown in the figure. Typically, with the stud punching outside diameter and the ratio D1 upon D. You can just see for the different kind of the rating provided by different operate different by method by reported by Lloyd and Tricky, who really work a lot for the single phase induction motor line. So coming to IC frame sizes and their other dimensions. So you can have typically the different dimensions which we really call it on the basis of typically as you look into the lower like 100L to 8. So that is for long length, stack length, then medium stack length and short stack length. These are the typical stack length and the different dimensions as is shown in the diameter as a typically the main dimensions as well as footing dimensions where you really mount these motors. Like so that the different if these are standard because you should be able to make any motor of any make of a particular rating that you should be able to fix up the motor or you can replace the motor, and it gives you standard dimensions for the typically selecting and designing the motor so that it really conversant with different this standard all the manufacturer correspondingly. Now you can call it. Now coming to the design of stator. Once the stator inner and outer diameter are fixed, the design of stator includes the number of turns in main and auxiliary winding, cross section area of conductor, number, shape and size of stator slot, depth of stator core and winding resistance. So coming to for the number of turns in main winding, taking a induced EMF expression equal to 4.44 F5M kWm into Tm, where M denotes the main winding. So induced EMF developed as taken as 0.95 V rated and the winding factor kWm is determined from the average factor of all the coils in the winding. So Tm is 0.95 V rated divided by 4.44 F5M kWm, where kW is usually 0.72 0.85 for main winding. Normally because we have here the normally the single layer winding, in general with the different kind, maybe a MS winding, and typical concentrated winding, half, unconcentrated winding. So different kind of windings are used, and this winding factor varies from the rating as well as the type of winding. So now typically going again for the relation of induced EMF 4.44 F5M kWA for number of turns in typical running winding or auxiliary winding. So its induced EMF is equal to 0.9. Similarly, we calculate for auxiliary winding. So we say a T equal to 0.95 V rated P divided by 4.44 F5 PID LKA. So now from diameter of main winding and auxiliary winding, we can find out dm equal to under root 4 by 5 a slot m into kfm, that is the space factor divided by nsm. And similarly, we can find out diameter of the conductor for auxiliary winding 4 by 5 a slot a into kfa into nsa. So where kfm sa are the desired slot fill factor for main auxiliary winding, and nsm and nsa are the number of conductor in one slot in main winding and auxiliary winding respectively. So coming to cross sectional area of the main winding and auxiliary winding, so it comes now ACM comes of main winding cross section IM upon your sigma m, and ACU equal to IC upon sigma c, where sigma m CSU are the current density used in main winding and auxiliary winding respectively. So usual current density that sigma m sigma c for normal conventional pulled motor are normally 3 to 5 ampere per millimeter square. You can find out the ACM will be HP into 0.746 divided by P into eta into cos phi into sigma m. Similarly, so now we can come to the number of stator slot. A large number of stator slot reduces the leakage reactance by reducing the slot and leakage reactance, resulting in higher output from the same frame size at better efficiency and power factor. So higher the slot number, lower the space factor. Number of slots in stator is a trade-off between the space factor and performance. And for single phase motors, the number of stator slots should be divided by the number of poles so that the balance and regular winding can be used. Now coming to size of the stator slot, all the stator slots do not have the same number of conductors, so and same and the some may contain combination of starting, running and main winding. So starting winding has a small cross section area and its affects the size of the slot is small because usually we use smaller cross section area so that we have a higher resistance and lower leakage reactance of the auxiliary winding, or you can call it the typically the starting winding. So generally running winding coil with largest number of turns determine the size of slot, and the slot liner is usually 0.3 to 0.4 millimeter thickness, and semi-closed tapered slot are used with the space factor of 0.35 to 0.4 because of the insulation of 2-3 level. One is the insulation with the liner, another insulation on the conductor slide. Now coming to size, for the size also there are NSM and NSA, number of the conductor of main auxiliary winding respectively in one slot. The area of the slot required here is AS equal to NSM 0.25 pi d I MSA square plus NSA 0.25 pi d di EA square divided by K fill, where K fill is the fill factor which is usually not greater than 50% for these motors because large insulation for both winding as well as on the conductors are there on these copper winding. Okay. The average slot width will be WS average by D, capital D plus DSS divided by SS minus WTS, where DSS is the depth of stator slot, WTS is the stator tooth width, and SS is the number of stator slots. So area of each slot will be WS average into DSS. Now coming to dimension of stator teeth, the flux density stator teeth will not exceed 1.8 Tesla. So BTS equal to 5 m divided by SS P divided by P into K STK into Li into WTS. And stator core, the stator core flux density used will not exceed 1.5 Tesla. So B is equal to 5 m into 2 KST into Li into DCS. So here the SS is the number of slot, P is the number of holes, Li is the 95% of stack length because of lamination structure, and KST is the stacking factor, and WTS is the width of the stator teeth, and DCS is the depth of the stator core. Now coming to mean turn length, the length of the mean turn for each of the coil per pole of the concentrated winding is LMT equal to 8.4 in bracket capital D plus DSS divided by SS into slot span plus 2L, and the length of the air gap length is found empirical, G equal to 0.007 into rotor diameter under root the power rating, and that's equal to 0.007 into DRO divided by under root P, where P is the power. So now coming to design of the rotor, the number of rotor slots is chosen so that there is no noise producing harmonic combinations, and it has been found that the quiet running motor results in if there is no harmonic field of the stator or rotor slot with number of poles differing by less than 4. And now these are for the design of the slot there are restrictions that how to avoid the NS should be less than 1.25 times NS to avoid the asynchronous torque, that's usually defined crawling, and R equal to not equal to 6P by 2 N, and avoid the synchronous torque at stall, avoid the cogging. NR not should be equal to NS, or NR not equal to 0.5 NS, and NR should not be 2 NS, avoid synchronous torque, and NR should not be equal to CP upon 2 N plus minus P, avoid the synchronous torque during running. Here N is an integer, so you can call it NR should not be NS plus minus P, NR should not be 2 NS plus minus P, and NR should not be equal to NS plus minus 0.5 P, and NR should not be equal to 0.5 NS plus minus 0.5 P, which avoids the typically avoids dangerous slot harmonics to avoid the cogging, crawling, and other physical phenomena like noise and vibration in the motor. So you can see there is a lot of restrictions typically coming out for selection of rotor slot. You got stator slots, that is NS, we decide on the how we put the winding related to the typically with the number of poles. So there are a lot of restrictions comes for selection of rotor slot. So you don't have it really so much choices really for selecting the rotor slot. So now other restrictions comes for avoiding the mechanical vibration is NR should not be equal to 6P by 2 N plus minus 1, and R should not be equal to 6P by 2 N plus minus P plus minus 1, and R should not be equal to 6P by 2 N plus minus P plus minus 1, and typically where the N is the integer. So you can call it selection of stator slot. As you look into, we have here typically you can see the if you are selecting NR equal to typically 24, 36 and 48, and how the number of poles pair and all that typically comes out. So all these restrictions, and finally coming to like on the right side of the table that you have a if number of poles are 2, 4, 6, 8, 2. So what should be the number of, if there are the stator slot, what the number of rotor slot you can select it for that. Like So these are the tables which give you design guideline to selection of the rotor slot for a given stator slot. Like, so only the combination without a symbol are safe choice. So these are disadvantage with all the combination. Minus means harmful torque as it is given in the left side table in the counter current breaking, and plus is the harmful torque in positive speed, and X is the harmful mechanical vibration, and 0 is the synchronous torque at the stainless steel cogging. So this define that what really the phenomena is there for different kind of slot combination typically. Now coming to rotor bar, the cage rotor winding may either be of copper bars or an end ring of cast aluminum, and manufacture of casted aluminum winding is cheaper than the copper winding because copper aluminum is having a density of 1/3 as well as the cost is also 1/3 per kg, so it comes around 12% cost of the aluminum compared to the copper for same volume. So total stator copper cross section for main winding is 2 nm into m, and now a high rotor resistance is desired for the standpoint of starting torque and current but leads to high slip and poor efficiency. So total copper section is generally 0.5 to 0.8 of the stator copper section. So copper section in rotor to stator is AR upon AM, that is 0.5 to 0.8. So AR upon AM equal to 1 to 1.6 for aluminum. That is usually typically the higher. So now coming to total cross section of bar, AR equal to NR into AB, where IB is equal to AB into JB, where JB is the current density in your rotor bar, and typically end ring current and area. End ring current comes I equal to NR into IB upon pi into P, and area of each end ring A equal to I upon JE, that is NR AB into JB divided by pi P into JE, and A equal to IE upon JE, that's it, NR AB upon pi upon PE. If JB equal to, typically you take the JE, that's current density of your, so you can call it AB equal to IB upon JB, and A equal to I upon JE, that's NR AB upon pi E. And considering that JB you can take equal to JE because we are using same material, and normally the cooling effect is also the same. So A can be upon JE into 0.32 into cross section of rotor bar divided by P, or 0.32 AR upon P. And you can see the different kind of the typical rotor slots. I mean, you can call it the deep slot, rectangular slot, you can call it slanty slot. These are the type of slot if you consider it typically order of what. There are many other geometry also which suits typically to avoid, typically you can call it getting a better starting torque as well as the running performance also. That really affect, I mean, by shape of the slots also. So now coming to rotor resistance, the choice of rotor resistance is important design of induction motor. So it should be low as possible to keep down the rotor losses and maintain the higher efficiency, high full load speed and minimum temperature. In case of single phase induction motor, there is an added advantage that the rotor resistance affect the maximum torque for a given flux, and therefore a higher value of pull out torque is obtained with large value of rotor resistance. And the minimum value of rotor resistance is dictated by the starting torque requirement, and higher the requirement, higher the value of rotor resistance to be used. Significant parameter is the ratio of Rm dash upon XLM dash, and here I am referred to the rotor resistance referred to the main winding. Xm is the sum of leakage reactance of main winding and rotor in terms of main winding. Now coming to rotor resistance empirically for split phase motors, the ratio RRM dash upon XLM is the range of 0.45 to 0.55, and for capacitor start motor this ratio RRM upon XM is in the range of 0.45 to 0.8 like. So actual expression of rotor resistance provided in subsequent slide. So the rotor teeth and rotor tooth and core density may be higher than that of the stator, as the frequency of the rotor is the slip times the stator frequency, because core loss is not there. So it's only affecting only the magnetizing current. How the excessive high flux density may lead to the increased magnetizing current. If WTR is the width of the rotor teeth, the flux density in rotor teeth BTR equal to pi m P upon NR into KST into L into WTR. So now rotor teeth and core plug, you can call it the BTR equal to pi m upon 2 into Li into DCR, where DCR is the depth of rotor core and Li is the 0.95 L. And now coming to effective air gap length, the flux density on the right side of the slot is slightly higher than on the left side, since the small current is flowing in the slot towards the observer. So you can see how really the flux concentration is there from the left side diagram. You can just see the behavior of air gap flux density along with which at the opening, and there is a local of the flux density. Now coming to effective air gap length, so distribution of air gap flux density B delta alpha is a distance from one slot pitch tau, and alpha is the angle revolving around the periphery of the machine as is shown on the diagram, and B is the equivalent slot opening, and the Carter FW Carter provided a solution to the problem of manual calculation. And on average, according to the Carter principle, the air gap seems to be the longer than the physical measure because of the slot opening, and length of the physical air gap, that is sigma, is increases with the Carter coefficient Kc, and the first correction is carried out by the assuming the rotor to be smooth. And now you can call it the effective air gap is GCS equal to Kc into G. So the effective slot opening to be B in which the flux density is 0, that is B equal to Kb, where the K is 2 upon pi arctan B1 upon 2G minus 2G upon B logarithmic under root 1 plus B1 upon 2G square, or approximately equal to B1 upon G divided by pi plus B1G. The Carter coefficient Kc equal to tau upon tau minus B, or tau upon tau minus K into B, where Kc equal to Kcs and Kcr. That is Carter coefficient for the stator and the rotor line. Now coming to the typically effective core length, so stator and rotor have the same stack length, no duct, so L equal to Li plus 2G or Li equal to Lis equal to Lir, as you can see in the figure. Typically, an stator and rotor slightly different core length and no duct, so L equal to Lis plus Lir divided by 2, or Lis is not equal to, or if Lis less than Le or less than Lis plus 2 8G, that typically you can see in the diagram. So now coming to the stator and rotor same stack length, same slot duct, so L equal to 2 L equal to Li plus 2G plus N in bracket your LOS plus LOR by 2 in bracket 5 upon 5 plus LOS upon G into 5 upon 5 plus LOR upon G. So where L equal to L1 plus L2 plus L3 up to L plus N, and then you can see what is L1, L2 typically for the. So having a stator, if as has a N duct, the rotor is smooth, so L equal to Le plus 2G plus N LOS in bracket 5 plus 5 upon LOS upon G, where L again L equal to L1 plus L2 up to Lin as seen in the diagram. So now coming to typically as a stator and rotor slot has N duct but are not screw, so L equal to Li upon plus 2G N upon 2 LOS in bracket 5 upon 5 plus LOS upon G plus LOR 5 upon 5 plus LOR upon G, Li equal to L1 L2 to Ln plus 1. Now coming to magnetic circuit calculation, these were the dimensions. So now magnetic flux produced by stator MS passes through the following path of a magnetic circuit, like air gap, stator teeth, stator core, rotor teeth and rotor core, the 5 parts through which the flux flows into the single phase induction motor. And now you can just see due to saturation teeth, the flux density distribution curve is flat top as explained earlier, as you can see here how it is the typical. Therefore, the calculation of MS will be based upon the value of flux density at 60 degree from the interpolar axis as far as gap and teeth are concerned. You can say total MF will be MF for air gap plus MF for stator teeth plus MF for rotor teeth plus 0.5 MF for stator yoke plus 0.5 MF for rotor yoke. As you can see in the diagram how the flux flow, path flow is there in different parts of you. So you have a typically stator core, then you have a stator teeth, then you have a air gap and rotor teeth and rotor core. So now coming to for magnetic circle, as approximated value of flux density at 60 degree from interpolar axis is 1.5 times the B average for single phase machine. So B60 is 1.57 B average. Time required for air gap will be 8060 into 800,000 B G60 into kg into G, and typically M4 of a teeth where there are NS slots in stator. So we obtain the slot pitch of the stator by dividing the air gap periphery by the number of stator slots. So tau u is equal to pi d upon ns. So magnetic voltage upon MF of a teeth is calculated at the peak of the air gap fundamental flux density, and when the tooth occurs at the peak value of the air gap flux density as the apparent flux passes through the slot pitch, so pi D peak dash equal to L dash into tau into Bg peak. So now you can see how the magnetic circuit, how the variation of typically the flux density and the fundamental flux density variation is there, like in the, so you will at actual flux density have certainly the dip because of the, you will find because of the air gap and teeth portion, slot portion and teeth portion, like in different kind of the slots. So opening and taking into account the space factor KFE of iron, so we obtain the tooth and uniform diameter cross section, that's Hg equal to KFE into Lb, and then you can call it the, assuming that the complete flux is flowing in the teeth, average flux density, so BD peak average equal to 5D peak divided by Hd, and that is Le into tau U divided by KFE L into BD into Bg peak. So in practice, as a part of flux is always flowing through the slot along with the area, so SU, which consists of air gap 2, denoting this flux by phi u peak, we may write a flux in the total iron phi d peak equal to phi d dash minus phi u peak equal to phi dash d peak minus Hu into Bu peak. So now by dividing the result of by the area of the teeth iron Hd, we obtain the flux, real flux density of the teeth iron Bd equal to Bd peak dash minus Hu upon Hd into Bd dash, where the Hu upon Hd equal to Les into tau U KFE LBBD minus 1. The apparent flux density Bd dash of the teeth iron can be calculated when the peak value of the fundamental air gap flux density is known. So real flux density in the teeth is thus Bd peak equal to Bd dash peak minus Hu upon Hd into mu 0 H d peak. So now to find out the point that satisfies the equation of Bs curve of the electrical steel, it's used for this machine, as you can see the diagram. I mean, this is a kind of material property, so you can call it the easiest way to solve the problem graphically as shown in the figure. How you are going to that Bd dash and all that. So Bd dash peak will be Bd dash minus Hu upon Hd into mu 0 Hd peak, and the MF of teeth is approximated by Hd peak into Hd. And typically the fit the Bs characteristic to get H from a function of B. So you will find Hb will be a function of K1 B5 K2 B4 K3 B3 K4 B square K5 B1 B power 1 and plus K6. If P is greater than 1.5 Tesla, if greater than less than 1.5 Tesla, then Hb can be K6 into e to power K7 B. So this is the way how we really model this magnetization characteristic for different portions, as it is shown here. Now coming to magnetic circuit technique to find out the intersection of the line on Bs curve of steel as shown in the diagram. To get the actual flux density, we have F and Hu slot area and Hd teeth area. You can say H equal to as a function of B average, Bf, and B equal to Bf. So B equal to Bf minus B mu 0 into pi into Hd upon H, Hu upon Hd into H, while the absolute value of 1 minus Bu1 is greater than 0.001, and Bv equal to B and H equal to F in as a F function of Bv, and B equal to B F minus mu 0 pi Hd upon H, Hu upon Hd into H, and B equal to 0.5 B plus Bv, and of course the end. So that is the way how you calculate the flux density. Actual flux density is typically in the slot area. Now coming to magnetic circuit calculation to find out the saturation factor for magnetic circuit. So a machine is dimensioned in such a way that the iron parts saturate at the peak of flux density. The flux density distribution is flattened, and in ordinary network supplied induction motor, both the stator and rotor teeth are saturated at peak value of flux density. As you can see here, how the typically the factor is responsible, saturation factor is responsible, that considering that alpha equal to 1.24 K saturation plus 1 divided by 1.4 to K saturation plus 1.5, and K saturation is MF for stator teeth plus MF for rotor teeth divided by M for air gap. So typically this leads to higher reluctance of the teeth, when compared to the other teeth, and the Li takes notably higher value than the value corresponding to the sinusoidal distribution. So factor Li has to be iteratively gradually to be correct value during the design process. So this become iterative from this diagram how we get for K saturation for given Li, L5. So now typically in practice Li equal to 0.77 is not exceeded. So this saturation factor simply takes the teeth into account. Because of this, possible saturation is the main reason for the flattening of the air gap flux density distribution. And these are typically the design equation where we use the administrative method to find out the saturation factor in the magnetic circuit. I mean, all these relation what we really talk about, they have been put in this, you can call it the program. Like, so now coming to typically the MF for variable teeth tooth width can be estimated using the summation of all the MF in the tooth in the previous pseudocode is given in a earlier slide. The principle of flux density distribution of non-film stator teeth, the absolute value of the field strength H and the iron loss density PF upon V on the integration path of the middle of the teeth. So these are the material property which we get from the dimensions and the type of material which are using in teeth as well as in the different parts of the stator and rotor line. So coming to typically the MF for stator and rotor yoke. So flux penetrating the air gap and the teeth section is divided into two equal parts in stator and rotor yoke, and at the peak value of air gap flux density on the D axis, the flux density in the yoke are 0. So minimum flux density for the yoke occur in the on Q axis on which the air gap flux density is 0. As you can see typically here, I mean typically the different portion, as we call it, D axis and Q axis, and the different distribution of the typically the flux integration path. So the behavioral flux density of the stator yoke and the strongly nonlinear behavior of the field strength H by S, which explain the difficulty in definition of magnetic voltage of the yoke. So ideal integration path is inducted by the thick black dotted line and the real integration path for any flux line, for example thick gray dot line here. So now the maximum value for the flux density of stator yoke can be calculated on the Q axis without difficulty, since the half of the magnetic flux flowing there. So P by S peak equal to pi m peak divided by 2 SS, or pi m equal to 5 m peak divided by 2 KFEL into HS, and that is for stator. And for rotor, B by R peak equal to 5 m peak divided by 2 SI S by R, or equal to 5 m peak divided by 2 KFEL into H by R. So where S, YS and H are the cross sectional area of the stator and rotor yoke, and KF is the space factor of iron, and HYS and HY are the height of the stator and rotor yoke respectively. So now coming to magnetic flux density of stator and rotor yoke, you can call it H. H peak is equal to H as a function of flux density in the YS peak, and similarly for rotor, HS peak equal to H as a function of the flux density in the peak flux density in the rotor yoke. So MF for stator and yoke can be calculated C into HS peak into tau YS, and MF for rotor is equal to CH YS peak into tau YS. So that is per unit MF multiplied the length of the magnetic circuit path. So coefficient C takes into account the fact that the field strength is strongly nonlinear in the yoke, and that the nonlinearity is stronger, and the more saturated in the yoke is at the Q axis. Like, so the coefficient is defined by the shape of air gap flux density curve, by saturation of the machine, and by dimension of the machine. Or the most decisive factor is the magnetic flux density in the yoke of the machine. So if there is a slot winding in the machine, the magnetic voltage of the yoke can be estimated by the curve illustrated in the figure. Next, so this is virtually, you can call it the coefficient C with the flux density in the yoke for stator and rotor, like how they are really getting affected, this coefficient C. So now you can call it no load current calculation will be equal to MF total plus MF equal to MF stator teeth, MF rotor teeth plus MF for stator yoke plus MF for rotor yoke plus MF for air gap. And no load curve of the machine thick line, as you can see in the diagram, and its composition of influence of stator teeth DS and the rotor air and the air gap G, and the rotor teeth DR, and the half of the stator and rotor yoke 1/2 YS and YR. These are the path of magnetic circuit in typically different parts. So total MF is sum of all the MF of all 5 parts. Now coming to no load current calculation, in some cases the whole magnetic circuit is replaced with the equivalent air gaps. Consequently, the magnetizing curve can be replaced by an operation defined by a straight line, dotted line. And note that the proportion of the magnetic voltage of the iron is strongly aggregated. So you can call it the equivalent air gap will be G equal to MF of total divided by MF of air gap to G, and magnetizing reactance will be XM 2 pi F mu 0 Li M D air gap L dash in bracket NS KWS squared by 2 P square into G, and magnetizing current at or no load current can be I magnetizing MF total divided to pi P divided by M KW1 N1 on root 2. And resistance of main winding, calculation of resistance and reactances. So resistance of main winding Rm equal to PCU into LMT into LM AM NM upon AM, and resistance of auxiliary winding Ra equal to PCU into LMT into Na upon AA. So now the resistance of the rotor RRM test for referred to the main winding 8 Nm into KWM square into rho in bracket LB upon R NR into AB plus 2 upon pi D upon P square AE into K ring, and K ring is the multiplication factor for non-uniform distribution of the current in the end ring, and stated slot leakage is your excess equal to 16 pi F Nm K KWM square into L upon KSTK into NS into lambda SS into CS, and where Cx is equal to Z1 square plus Z2 Z3 square divided by Z1 plus Z2 whole square into K1 upon Ksm into NP Ns upon 4 pi P, where Z1 Z2 are the number of conductors in different slots, and there are 2P groups of Z1 Z2 and Z3 conductor per slot. So now coming to the rotor slot leakage reactance in terms of state slot leakage. So XSR that's equal to 16 pi F in bracket Nm KWM square into L upon Nr into lambda SR. So total slot leakage in terms of on state side XS equal to XS plus XR, it will be XS equal to 16 pi F Nm KWM square into L upon Nr in bracket Cx lambda SS plus Nr upon Ns upon Nr into lambda Sr. So leakage zigzag reactance is XZ equal to 16 pi F in bracket Nm KWM square L upon Ns into lambda Z, where the lambda Z is equal to specific perimeter of zigzag leakage, and overhang leakage is equal to X0 equal to 16 pi F Nm KWM square L mu 0 divided by 6.4 NSP in bracket pi capital D plus small TSS into average coil span in slots. So now coming to skew leakage reactance, XSK equal to XM theta S squared by 12 Ki, where theta is the rotor bar skew angle, that is equal to pi P upon Nr into rotor slot pitch for which the bar are skewed, and K1 equal to under root XOM minus XLM upon XM. The slot skewed leakage factor, that is approximately 0.95, and XM is the magnetizing reactance. Now total leakage reactance XLM will be equal to XS plus XZ plus X0 plus SFK, and open circuit reactance referred to main winding will be XM equal to XM plus 0.5 XLM. Now coming to iron loss calculation, the iron loss in the stator teeth and core is found by calculating their flux density and weight. The loss per kg can be calculated for using the B versus P characteristic of the paramagnetic material used at a particular frequency for designing the stator teeth and stator core. So in manual calculation, the iron losses are found by dividing the magnetic circuit of the machine into n sections, and with the flux density is approximated constant, and once the mass is M FEN of the different area and has been calculated, the losses PFN of different parts of the machine can be approximated as follows. The summation of losses in individual segment of iron as PFEN equal to summation 1 to n Kf into P15 in bracket Bn Kp divided by 1.5 T into M FEN. So where P15 is the loss of the steel at 1.5 Tesla at a given frequency, and MFEN is the mass of individual iron segment. So now furthermore, the stresses created in the punching of the steel and also the burst increase the loss index. In manual calculation, these phenomena are empirically taken into account, and the iron losses can be solved by taking into account the empirical correction coefficient Kf defined by different sections. So correction coefficient Kf for the different of the definition of iron losses in different sections of different machine types, taking into above anomaly into account. Machine type like a synchronous, asynchronous machine, typically T typically is a 1.5 to, so in yoke it is 1.5 to 1.7. So now coming to friction and windage loss, the bearing friction and windage loss depend upon the type of bearing to be used. whether the bearing or sleeve bearing, and it is usually 4 to 8% of the watt output. And Squeezkey in 1960 gave an experimental equation for the summation of windage and ventilator losses, that is P equal to Kp dr in bracket Lr plus 0.6 tau P to V square. So, or you can call it that V equal to Kp pi dr in bracket Lr plus 0.6 tau P into Vr square, where Kp is the experimental factor mentioned in table below, and dr is the rotor diameter, Lr is the rotor length, and Tp is the pole pitch, and Vr is the surface speed of the rotor, or you can call it the peripheral speed. So, for different motor, this value of the Kp watt second square per meter power 4 is typically varying from 5 to 15. Now, coming to straight load losses, the additional losses called also straight load losses are defined as the difference between the total losses and sum of straight and rotor, resistive losses, stir and iron losses, and the mechanical losses, all measured or calculated from the results according to IC 60034 to 1 standard method for determining losses and efficiency form test. So, this you can call it straight losses, which are not accounted as a percentage of input power. It is just calculated for different scale gauge machine. It's order of 0.3 to 2%, sometime up to 5% of input power, and 4 other machines are also given. So, now coming to according to IC 60034 to 1 in and 2007, PLL equal to 0.025 PN, where P out is less than 1 kilowatt and PLL equal to in bracket 0.025 minus 0.005 logarithmic 10 P out upon 1 kilowatt in for 1 kilowatt output, power output typically less than 1, greater than 1 kilowatt and less than 10 megawatt, and PLL equal to 0.005 P in for power output more than 10 megawatt. So, usually this single phase motor is in first category, where PLL equal to 0.025 PN. So, that's order you can call it about 2.5% of input power. Now, coming to performance calculation of this single phase induction motor. So, running performance of single phase induction motor can be calculated by two methods: equivalent circuit method, double revolving theory, or V-nut method, that is analytical method. The equivalent circuit method, the typical equivalent circuit is determined by double revolving field theory for any slip S, where forward torque is IF square RSM upon 2 S, as we talked in the last lecture, as the equivalent circuit is given, and backward torque is IB square RRM divided by 2 into bracket 2 minus S Singh and Singh watt, and gross motor torque is RRM squared by 2 RF IF square 2S minus IB square 2 upon 2 minus S in synchronous watt. So, this equivalent circuit net motor torque is gross torque minus iron plus friction plus windage loss. However, the analytical method by V-nut, the V-nut method can be applied if parameters of equivalent circuit are available. Specify the typically HP rating, line voltage and speed, and calculate the following motor constant. So, here it is given like typically for analytical method how you can calculate the typically RSM as a function of F1 equal to 2 minus K1 per RRM is and RM square F2 2 minus S. So, all these K1 are 2, and you can find out even magnetizing current, as well as you can find out the typically the other losses. Typically here all the by this analytical method you can find out the entire performance like. So, other typically the formula for calculation by this analytical method like. So, all the let's say input power, output power, all the calculation are made by these empirical relation by V-nut, who really have a first computer design of electrical machines book virtually, and lot of work on this, especially for single phase motors, induction motors, so they are used very widely. So these are the all the formula given by the V-nut, like analytical formula for calculation of complete performance in terms of equivalent. Now, coming to example of performance calculation of the single phase by V-nut method. So, you can call it now performance single phase induction motor obtained from the classical theory, which are efficiency power factors, input power, output power, and starting torque, and are compared with the constant done by V-nut theory. The specification of the outer single phase motor are given here for a power of 370 watt, typically output power of half HP, then the voltage of 230 volt, 50 Hz, and 4 pole motor with the starter slot 36 and rotor slot of 44. This is typically taken from the kind of research exercise, and equivalent circuit parameters are given here, starting typically from voltage and your stator leakage overhang, then the resistance stator and rotor resistance referred to stator, then the factor, then the other parameters, all equivalent circuit parameter, and then the typically the magnetizing current, and then typically the your magnetizing drop and then typically all the formula are tabulated by according to Binot curve calculation. So all these formula are used for the making a calculation typically of different parameters in terms of performance parameter, either core loss component or core loss and friction and windage losses. And then typically here the all formula are given with the calculated value, putting the value in the formula for this Binot method. And as you can just see here, the power factor and efficiency all are calculated for that half HP motor given typically the specification there, which are taken from typically from this paper. And the total losses of stator rotor couple loss, windage loss, total iron loss, and efficiency finally. So now coming to theoretical problem. So question 1: what factor influence the selection of number of stator slots and winding turns in single phase induction motor? The answer is the number of slots and winding turns are influenced by power rating, voltage and current requirement, guide and choice, and other considering factors like magnetic flux density, slot fill factor, and winding distribution. The question is that question 2 is what is the type of rotor? Skull cage important in case of single pole motor. The choice such as skull cage rotor ensures simplicity, robustness, and efficiency, making it suitable for various applications. The question 3: how does the magnetic circuit impact the performance of single phase induction motor? The magnetic circuit influences the flux distribution and efficiency, with factors like air gap dimensions and material property of the stator core being crucial. So question 4 is why the ventilation and cooling vital in single phase induction motor, and how it can be addressed. To adequate cooling prevents the overheating, ensuring optimal performance and extending the motor lifespan, and proper design includes the ventilating ducts and cooling fans. Why the rotor slot do not start and run capacitor play a single phase induction motor, and how they are sized. So start capacitors and aid initial startup, and run capacitor optimize the power factor during normal operation. So sizing consider motor specification and torque requirement. So what are the considerations are essential in designing the winding layout of a stator rotor? So coil pitch, distribution, and minimizing the harmonics are the crucial for optimizing the motor efficiency and performance. So question 7 is why the material selection important in designing single phase motor? So material impact the magnetic and electrical property. So power selection of stator core, rotor, and winding ensure desired performance. Question 8 is what are the factors need to be considered in selecting bearing and designing the bearing housing? The suitable bearing and proper housing design are crucial for optimum motor performance and longevity, and lubrication requirements should be specified. Question 9 is how can a single phase induction motor be optimized for high efficiency and power factor? So minimizing losses, proper winding design, and considering core loss and winding material contribute to achieving high efficiency and power factor. The question 10 why is the testing and validation important design process of single phase induction motor? Testing ensures the motor meets the design specification of efficiency, power factor, torque, field characteristic, and compliance with the standard. Now coming to numerical problems. So the question 1 is to calculate the main dimension of a 370 watt 230 volt 4 pole 50 Hz single phase induction motor. Single phase capacitor start induction motor. The full load efficiency and power factor should not be less than 0.62 and 0.65 and 0.2 respectively. So here actual speed is 1430 rpm and the synchronous speed is 1500 rpm like it in RPS 25, and watts per RPS is 370/25, that is 14.8. So value of C0 and eta cos phi is 16.5 for a watts per average of 14.8. Now the product D square L is now KW upon C0 and eta cos phi and S, that comes putting the value, it comes 0.897 10 to the power minus 3 meter cube, and considering the L upon tau 1, so we have L equal to 0.785 D. So thus we get, putting in this equation of output equation, 0.785 D cube equal to 0.897 10 power. So D comes 0.1045 meter and L comes 0.785 D, that is 0.0820 meter. Now coming to question 2, for a 370 watt 234 4 50 Hz single phase capacitor start induction motor, have a motor bore diameter of 104.5 millimeter stack length and stack length is 82 mm. Calculate the flux per pole and calculate the stator back core flux density for a frame outer diameter 181 millimeter. There are 36 slot in stator and stator tooth width is 4 millimeter and the slot depth is 19 millimeter. The width of the stator tooth is given as 4 millimeter and taking a flux density for stator teeth as 1.1 Tesla. The flux per pole will be phi m equal to BTS into NS upon P into Li into WTS. So putting value it comes 3.084 milliweber and depth of stator core DC is equal to D0 minus D minus 2 ds by 2. Putting value it comes 17 millimeter and flux density in the stator core comes BC is equal to phi m upon 2 Li into GS. Putting value it comes 1.1 Tesla. Now coming to the question 3, calculate the main dimension of 1500 watt 230 volt 50 Hz for pole capacitor run single phase induction motor. The power factor and efficiency of the motor should not be less than 0.95 and 0.8 respectively. The value of expected ratio should be considered so that the flux density does not exceed 1.4 Tesla and 1.8 Tesla. The number of stator slots should not be greater than 36. Calculate the number of turns required for main winding the specified motor. If the permissible current density of the main winding is 4 ampere per millimeter, calculate the wire gauge of main wire and slot fill factor should not exceed 50% in question insulation. So now coming to the typically the solution. So watt per RPS for this machine is 1500 watt divided by RPS 1500 by 60, that comes 60. And from the typically table for watt 60, the C0 and eta cos phi is 43.465. So for by exploiting the initial value of linearity, we obtain y equal to find that with this linearity. So d square L comes P upon C0 and C0 eta cos phi. Putting value it comes 1.38 0 to the power minus 3 and considering L upon tau of 1, so L comes 0.7853D and D. So from this we get D equal to 0.1206 millimeter, L equal to 0.0947 meter and WTS is by D plus DSS is by typically number of slots into 0.3, so it comes 3.288 millimeter and the phi, putting this typically flux density all dimension comes 5.004 10 power minus 3 Weber and By is typically here 0.4. So from there we can find out the DCS from this relation. So we get the DCS equal to 19.02 millimeter and for taking a winding factor Kw equal to 0.8. So Tm comes, putting value in that relation, 0.95 into voltage divided by 4.44 F into winding factor into typically the flux. So it comes typically 244 tons and tons per pole comes now 61 by tons per pole. So stator slot per pole comes 36 by 4, that is 9. And this is the typically winding arrangement how we are putting here for one pole pitch. The winding, how we are starting, how we are ending. This is concentrated winding usually we design for this motor. And the details of this winding calculation according to that diagram is there, how it is really coming for 1 to typically 9 slots and then to second slot to third slot, and the total typically comes the winding factor as net for 2.8835 combined turns. So combining all this relation with it comes the sum as 61 slots by putting this all as a kind of percentage. Now winding factor from this we can find out by multiplying the number of turns and these factors. It comes 0.79068 by and Kw that's 0.7906 or 0.8, quite close to our estimated value, and Im is typically the motor current is P output divided by voltage into power factor into efficiency. So it is 8.5 12 ampere, where the if we take a current density of 4 ampere per meter, so area of the conductor will be pi d upon 4, that is 2.1453 millimeter square, and where the d comes diameter of the conductor comes 1.6525. So a slot is equal to a copper upon fill factor, and putting the value we get typically 90.1 millimeter square. And now coming to question 4, design a 1 HP 230 2850 RPM 2 volt 50 Hz split phase induction motor, and some useful data are given in the table below here, like typically the frequency and KF factor, table 2 with the output coefficient with the pole, and third is the your aspect ratio Ti upon Td for the different poles. Of course here we have a 2 pole, so obviously we will be using the first data itself for corresponding to 2 pole. Now so coming to the calculation of main winding, as for 50 Hz the frequency constant is Kf equal to 0.96 from table 1, and output constant volt C0.32 from table 2, and type of split phase type KT equal to 1.42. Now we can find out D square L equal to, putting the value in this output equation, it comes 2525.5 centimeter square. So now taking a L upon D0 ratio 0.3, we can find out outside iterator core diameter D0 equal to cube root of D0 square L upon D0, and putting value it comes 20.34 or 20 centimeter. So iterator core length is 0.3 D0, that's typically come 6 centimeter. Now inner diameter of iterator core Di equal to 0.5 du, and it comes 10 centimeter using the table third. Now typically assuming iterator slot equal to 24 and slot cross section area at a result teeth. Now slot opening at tip is ratio B10. From using this formula it comes 0.243 centimeter, and that slot opening as 10 is 0.707 centimeter. For single phase motor depth mouth of H11 that comes 0.091 centimeter, and width of the tooth comes BTR equal to, putting into the relation it comes 0.59 centimeter. And assuming plug density of iterator teeth 1.35 Tesla and iterator core 1.15 Tesla, iterator core depth can be found out from BT upon BC. From this relation it comes 2.64 centimeter, and width of the iterator slot by putting the value in this relation comes 0.7611 centimeter, and depth of the iterator slot H14, putting the relation it comes 2.1934 centimeter, and half slot angle and binarity upon S1 it comes 7.5 degree, and slot width at the bottom E1, putting the value it comes 1.3387 centimeter, and using unparalleled length of the air gap LG equal to, it comes 0.42 millimeter. Now coming to design of main winding. So number of coils per pole here is S1 upon P into 2, so putting value it comes 6, and using the concentrated winding, typically here for the different coils of 1 to 6, how really slot span and factor, and then how pitch factor is calculated here, like typically, and total pitch factor like. So now from that, taking all the factor into account, we can calculate the winding factor, summation of pitch factor in number of turns, so it comes like 0.7892. And now coming to design of main winding, considering the iron factor of 0.93, net iron core length is K into L, that comes 5.58 centimeter, and slot per pole is here S1P, that is 24 by 2, 12, that comes 12. Area of the teeth comes PT1 into Li into S upon P, comes 39.5064 centimeter square, and flux per pole is putting value here in this relation, it comes 0.034 Weber, and considering the induced EMF 0.94 V, the number of series turns in main winding 0.95 into voltage divided by 4.5 into flux per pole into kW, it comes 368 turns. Total number of conductor in main winding 2 into Tm, that's 2 into 368, 736, and number of series turns in main winding Tm upon P, that comes 3 by 2, 184. Now turns in each coil, so coil number 1 to 6 and percentage turns are typically put according to this distribution as calculated from this. So first coil is TCS, so here it comes around 44 turns, and for an ampere power factor is taken 0.6 and efficiency is 0.7. So current in main winding from this power relation and efficiency and power factor and voltage, it comes 7.02 ampere. Assuming current density of 4.5 ampere per meter square, so area of the conductor IM upon CDM, so it comes around 1.5601 millimeter square, and diameter of conductor under 4 into H pi, it comes 1.4094 millimeter square. So now coming to bare diameter of this suitable conductor is 1.42 millimeter, and considering enamel insulation it 0.075. So diameter of insulated conductor comes adding both to 1.4975 millimeter, and area of cross section of copper in the conductor is pi d mc square by 4, so it comes 1.5837 millimeter square. Now current density in main winding is Im upon mc, so it comes 4.43433 ampere per meter square. The space occupied 44 insulated conductor in slot, putting value it comes 0.7724 centimeter square, and area cross section of cross slot, putting all the dimension it comes 2.3486 centimeter square, and space factor for slot, putting value it comes 0.389, and height of the iterator slot, putting value it comes 2.2 2844 centimeter square, and length of main turn calculated. So suitable pair diameter TMC 1.42 millimeter, and considering LML insulation of 0.075 millimeter. So diameter of insulating conductor is your 1.497 millimeter, and area cross section of copper in the conductor is by DMC for by 4, it comes 1.5837 millimeter square. So current density in main winding comes IM upon typically putting a value, so it's 4.433 ampere per minute square, and space occupied for 44 insulated conductor in slot. Putting value would come 0.7724 centimeter square, and area cross section of cross when putting all the dimensions here, it comes 2.3486 centimeter square, and space factor of slot putting value comes 0.3289, which is less than 0.5, hence it is considered satisfactory or acceptable. The height of the stator yoke putting dimension H11 and H14 comes 2.2844, and mean turn length for each coil is calculated here 1 to 6 coil. Example for first coil is 8.4 di plus hs divided by into slot span plus 2 into L, and it comes like 63.59 centimeter. So mean turn length of main winding LMT into TN, so it comes 47.705 centimeter. The resistance of main winding is 75 degrees centigrade. Putting the resistivity LMT and TM MC into 100, it comes 2.328 ohm, and copper loss in main winding M square RM, that comes 114.74 watt. So rotor diameter here di minus 2 lg, it comes 9.9146 centimeter, and assuming rotor slot 30, the width of the tooth at the section it comes 0.4484 centimeter, assuming slot opening 0.075 centimeter, and depth of the tip is 0.08 centimeter. So now radius of round slot, typically considering that, it comes 0. By this formula 0.2594, and diameter of rotor conductor, putting the value of this in this formula, it comes 0.4808 centimeter, and suitable conductor standard wire gauge is 6 with the width with the diameter of 4.88 millimeter, and area of the conductor is 5 drc square by 4, so it comes 18.7038 millimeter square, and rotor core depth DC 2 0.95 DC1, that comes 2.5133 centimeter, and design of rotor length of the bar per conductor is L plus 1, so it comes 7 centimeter. Area of cross section of hand rings and B into AB upon pi BP, it comes 89.304 millimeter square. Resistance of the rotor winding at the 75 degrees is referred to main winding, P into MI square KWM square into resistivity 0.021 in bracket LB upon AB into LB plus 0.64 dm upon P square DER. Putting value all this, it comes 3.5359 ohm, and equivalent rotor current I to D, that is IM into PFA, so it comes 4.6335. Rotor copper loss ID square into RMD, so it comes 79.92 watt, and weight of the copper typically of rotor copper when putting all the dimension and density, it comes 0.3496 kg, and weight of the rotor steel and putting all these, it comes 3.3164 kg. And now coming for ampere turns calculation, so slot opening by air gap, it comes 5.6911. So Carter coefficient from the figure, it comes like typically 5.4, this is a 0.6445. So slot pitch by ds upon s1, that comes 1.3039 centimeter, and slot Carter coefficient putting a value sp1 minus this, so it comes 1.1359. and similarly for rotor slot opening divided by air gap, so it comes 1.75, and Carter coefficient for from the figure, it comes 0.3065, and calculating slot from there putting value pi d r upon s2, so it comes 1.0383 centimeter. Now stator slot coefficient kgr, that putting value sp2 in this level 1.0226, and air gap area pi di into pf into l, it comes 94.246 centimeter square, and air gap coefficient Carter coefficient for this, it comes kgs into kgr, so multiplying this one, it comes 1.1616, and air gap effective length comes kg into lg, it comes typically 0.0496 centimeter. So flux density and gap 5 into 10 power minus 4, and putting this area, so it comes like 0.5659 Tesla, and ampere turns for this air gap is from this typically giving flux density come 259.5 ampere turn, and area of steel in pole Li into BT1 S1 upon P, so it comes 39.5064, and flux density stator teeth, typically putting the value, it comes 1.3535 Tesla. So from for impedance calculation from magnetization characteristic, you can get the turn, typically the impedance per unit length, that is 467.7 ampere turns from the figure, and length of turn is typically given here, that comes 2.3544 centimeter. So impedance will be multiplication of specific into this length, so it's 111 ampere, and area stator core Li into GCS, it comes 14.7623 centimeter square. So flux density stator core is typically comes 1.1507 Tesla, and for this flux density, the per unit ampere turns per meter comes to 59.9 ampere per turn, and length of the flux path is here calculated typically from this formula, it comes 13.63, and ampere turns, this is specific into length of magnetic circuit, it comes 34.74 ampere, and area of rotor teeth per pole, ATR from Li BT2 into S2 by P, it comes 35.5311 centimeter, and flux density here from this relation of flux and this area, it comes 1.4211 Tesla, and for this flux density specific ampere turns from this characteristic magnetization characteristic, it comes 640.4 ampere turns per, and length of main turn in this case from LFT P2 of magnetic circuit, it comes 0.6 centimeter. So ampere turns for this specific ampere turns multiplied the length of magnetic circuit path, it comes 3.83 ampere. Cross section of rotor core Li into DC, it comes 14.024 centimeter, and flux density in core, putting value of this area into the relation, it comes 1.2112 Tesla. Now for this typical flux density, specific ampere per from magnetization characteristic is 304.15 ampere per meter, and length of flux path in the rotor core from this relation comes 2.444 centimeter. So ampere turns is your specific ampere turns multiplied the length of the magnetic circuit path LFT by 100, so it comes 7.4243 ampere. So total ampere turns required is ATG plus ATT1 plus ATG plus AT2 plus ATC3, so it comes 316.5 ampere, and saturation factor ATT upon ATG, this calculated 1.22. So now total, so from this leakage reactance calculation, this is Cx equal to, as a distribution of all, it comes 0.99261, and typically the ratio V1 that comes 0.56686, and constant from the figure you can kind of, for this ratio it comes 0.558. Now slot leakage, it comes by putting this relation, so it comes 1.3836, and rotor slot constant, it comes 1.6897, and slot leakage on S1Cx by this relation comes from 2.6331, and flux factor by putting value, it comes 1.0601, and slot leakage from the relation comes 1.7529, slot tooth phase, it 1.067 from the relation, rotor slot phase comes 0.9633, and zigzag coefficient by putting these all dimensions comes 0.4386, and zigzag reactance in this formula, it comes 2.2811 ohms. Now average coil throw of the coil stator winding, and from this relation for 6 coil, calculating putting all value, it comes like typically 8.3, we can have to be integer, so it can be approximated 8, diameter of the core I comes with this relation comes 12.5154, and the end rate leakage reactance from this putting the all these, it comes 2.733 ohm, and form factor putting this value, it comes 778.96. Now average slot pitch, S1 plus S2 upon 2 pi is 13.5, corresponding to this NS becomes 13.5, and band leakage comes 1.3346. Band leakage is by putting formula, it comes 1.0237, and rotor slot is to angle 15 degree, and the factor pitch factor 0.97, so total Q factor is 0.5 is Q square divided by 100, it comes 0.0056. Now slot SQ leakage reactance from putting this value, it comes 1.1471. Total reactance of main winding comes XS plus XZ plus XC plus XB plus SQ, it comes putting value 8.9378 ohm, and Q factor from this calculation putting value, it comes 0.9971, which is used for this calculation. So magnetizing reactance, it comes Kx into KMKSK, putting value it comes 209.63, and open circuit resistance XM. Reactance is XM plus XM by 2, so it comes to 14.1, and magnetizing current is V0 by X0, so this comes typically 1.0743 ampere. Assuming transmission ratio 1.6, the winding factor for auxiliary winding is 0.83, and using considered winding, number of turns auxiliary winding is KTM equal to 560 to round off, and number of conductors now comes 2 into that 120, and turns in auxiliary winding is T upon P, that's a 280, and page factor for considered winding quadrature to main winding. So here it is the design of auxiliary winding for span for all 6 coils and slot span and factor, and then the pitch factor calculation for average, and the number of turns in different coils. And then typically for the first coil example is given here, so it comes 62, and winding factor from this calculation comes 0.8253, which is of course 0.7284, so hence it is okay. The actual transmission ratio putting value here comes 1.5912, and length of, for coming to length of mean turns for all the typically 6 coil is given here, and you can find out the average. First coil it is given the relation here, and for similarly you can calculate for similarly for auxiliary mean turns length it comes 50.76. So now you can call it, assuming the cross section area of conductor for auxiliary winding is 12%, that of main winding of 0.2, so this comes putting value 0.19 millimeter square, and diameter of conductor is 104 into h by 5, it comes 0.4919 millimeter, and suitable diameter of bare diameter is 0.508 millimeter, and area of cross section of copper in the conductor is pi d AC square by 4, that comes 0.2027 millimeter square. The resistance of auxiliary winding is 75 degrees centigrade. I mean, putting the value here, it comes 29.4503 ohm, and rotor resistance in terms of auxiliary winding, refer to that, it comes typically 8.9524, and total resistance in auxiliary winding R1A plus RDR, it comes 38.4027, and total resistance of main winding similarly referred from rotor and main winding at 5.8638 ohm. The total linkage reactance of auxiliary winding K square electron, this comes 22.6292 ohm, and logged impedance of main winding RMT square plus electron square, it comes 7.6897 ohm, and logged load impedance of auxiliary winding RAT square electron square, so it comes 44.574 ohm, and then starting torque V square by putting this relation comes 1.737 Newton meter. Similarly for logged rotor current for starting for auxiliary winding, it comes 5.16 ohm, logged rotor current for main winding comes putting value V upon ZLM 21.516 ampere, current density auxiliary winding IS upon this comes 25.46 ampere per meter square, and so okay, it is less than 30, and weight for auxiliary winding copper putting value for LMT AC TA into typically the density 8.9 10 power minus, this comes 0.5127 kg. So now coming to question 5, design a 373 to 20 50 Hz 4 pole 50 Hz permanent split capacitor type induction motor, assume the required data. So main dimension of stator frame is based off the ratio of motor and giving the due consideration to all the factor. Following value are assumed for the design constraint: d square L and from typically 16.530 HP upon RPM into KF KT 10 power 6. The output coefficient C0 8.26 Tesla, frequency constant KF 0.96, and value of coefficient K at T equal 0.42. So d square L from this relation comes to 249 centimeter cube, and the most favorable portion between D and L is 0.3. So you can find out L 0.3 T. So D0 comes 19.57 centimeter, and considering that D this 20 cm, so L comes 6 centimeter. So the ratio of instrumental diameter to this Ti upon Do is 0.59 for 4 pole. So total internal diameter is your 12 centimeter. Number of history slots are 24. So parallel sided slot width are used to present case. So slot opening for motor of 24 slot opening is B10. When putting this relation, it comes Pi equal to 12 centimeter. Therefore, B10 is 0.278 centimeter. So depth of the pit slot is H equal to 0.07 considering that value, and depth of the mouth may be assumed 1 to 1.5 times the depth of the tip, assuming this ratio is 1.3, so depth of the mouth is at 0.3 into 0. So this comes 0.9 centimeter, and width of the teeth from this relation comes 0.77, and stereo core depth TC1 from the relation comes 1.94 centimeter. Then the width of the slot at the top section, there is the parallel side slot, trapezoidal slot with the flat portion, comes V11 from this relation by 0.77 centimeter, and width of the slot at the bottom and from this relation comes 1.27 centimeter. Length of the air gap LG from this relation comes 0.0382 centimeter. Now coming to design of main winding, the main dimensions and all the details of stud punching have been decided above. With these details, the next step is to design the proper main winding for the motor. So coming to now winding factor, the type of winding used for motor is concentric. So standard distribution of the winding reduces the harmonics in the air gap wave to minimum. So number of stud slot is 24. So number of slot per pole is 24 by 4, that's 6. The number of coil slot per slot is 3. So winding factor from this relation we can calculate, that comes 0.7988. Now total flux per pole from this relation, we put it comes 2.34 milliweber, and number of turns now you can calculate from induced EMF equal to 4.5 m, so it comes equal to 530 turns, and number of conductors main winding, that turns into 2, that's 1060. Number of turns per pole, that 530 by 4, 133. So number of turns in various coils of winding, number of turns in series pole, that is 530 by 4, 133. So maximum number of main winding conductor is in slot 59. So size of the conductor is a current in main winding I1 HP into 4, efficiency eta into V into cos phi, that comes 4.2. And now taking current density 4.5 ampere millimeter, so area of the main winding comes your typically the current divided by current density, it comes 0.93 millimeter square. So diameter bare conductor is here 19, standard wire gauge is 1.02. So with the enamel, with the addition of diameter 0.075 millimeter, so insulated diameter is typically 1.095 millimeter, and the number of turns in series per pole is 126. Now gross slot area, putting all the dimensions, comes 1.98 centimeter square. The space occupied by 59 strands of insulator of 1.095 comes, the space is occupied by, putting this formula, it comes 0.556 centimeter square, and space factor of the slot by putting this all insulator and cross, it comes 0.28, around 3. The space factor of 0.34 slot is quite self-factory. Now coming to resistance of main winding, the length of mean turns of each of the coil per pole of constant winding is given from this LMT, 8.4 di plus hs upon h1 into slot span plus 2 dl, and the height of the slot from this relation. So LMT comes by putting all these relations 33.98 centimeter. And now taking total turns calculated already 1530. So resistance for main winding R1, putting rho LMT LTM upon AM 4.66 ohm, and copper losses in main winding IM square RM, that comes 82.2 watt. Now main dimensions of rotor length of air gap is 0.0382 millimeter we calculated. Now internal diameter for stator is 12 centimeter. So now coming to typically main dimension of rotor, outer rotor is dr equal to di minus 2lg, so 11.924 centimeter, and rotor core length is now say for 11.6 centimeter on left. Now for number of rotor slots should be chosen so as to avoid the clogging cups and minimize the noise and vibration. The best number of rotor slots then selected will be 36. So number of stator slots here are, rotor slot is 36. So now detail of rotor punching, the width of the teeth BT2, by putting the relation 0.95 S1 BT divided by S2, it comes 0.54 centimeter. So slot opening present in this case B20 0.075 centimeter, and depth of the tip S20 0.08 centimeter. So now radius of the round slot R21 from this relation comes to 0.22 centimeter, and conductor diameter from this relation comes 0.402 centimeter. So nearest standard size is 8 standard wire gauge, whose diameter is equal to 0.406 centimeter. So area of the rotor conductor is 13 millimeter square. Now coming to rotor core length, the rotor core length depends on, may be taken approximately 95% of the stator core length. So thus the rotor core depth is DC2, which now comes to 1.842 centimeter, and equivalent resistance of the rotor to the referred to the stator is R2M square. Putting the value, it comes to 6.785 ohm. So now number of conductors in main winding is NO equal to 1060, winding factor for main winding K 0.7998, and number of rotor bars is 36, and the allowance is going 1 centimeter. So gross core length is 6 centimeter, length of the rotor bar is 6.17 centimeter, area of the bar is 13 millimeter, outer diameter dr equal to 11.92 centimeter. So now coming to details of rotor punching. Based on the outer diameter of rotor, the mean diameter of the end ring is dm equal to 7 centimeter. So area of end ring A equal to 1 upon pi np, 1 pi into AB, that's 37.24 millimeter square, and the equivalent rotor current I2 is I1 cos phi. So it's 4.56 to 2.604, and total copper loss is I square R2M, so that comes 46 watt. Now coming to performance calculation, to complete the design computation of core copper and iron loss is required. So core losses can be calculated exactly in the same manner as for 3-phase inductor. So core loss in stator teeth is flux density in stator teeth, BT is here is 1.3 Tesla, which is calculated, and number of stator teeth is 24. So area of the stator teeth is calculated from the dimension of it comes 4.72 centimeter square, and height of the stator is 2.06 centimeter. The volume of all stator teeth is the number of stator teeth at 24 into the dimension, so it comes to 33.36 centimeter square. Density of material 7.8 gram per centimeter cube. The width of the all stator teeth, from this relation weight of all stator teeth comes from this relation comes 1.82 kg, and thus the total core loss in stator teeth is from specific loss per it comes 11.1 watt. Now coming to core loss in stator core, the flux density in stator core already we calculated, it comes 1.08 Tesla, and sectional area of stator core is 10.83 centimeter square. So mean diameter the core is calculated from typically from it comes 18.06 centimeter. The volume of stator core from this relation we get the 614.46 centimeter cube, and weight putting the density here it comes 4.79 kg, and core loss for this flux density calculation for specific loss it comes with this multiply this volume, it comes 19.65 watt. Now coming to surface losses, total and loss due to fundamental frequency flux when calculated here with the two, it comes 30.75 watt, and surface losses may be assumed approximately 90% of this, so it comes 27.68, and total loss putting both it comes 58.43 watt. So bearing friction based loss depends upon the type of bearing load, bearing and peripheral speed as we already discussed, and it is around 5 to 8% of the output. So friction voltage considering 5%, so it's 19 watt. Now copper loss calculation for forward impedance, it comes 65.3 at the angle of 54.72 degree ohm, and ZB from this calculation comes your 3.56 at the angle of 63.46 ohm. So from here we can calculate the current drawn by the motor from mains I1, that comes 3 ampere, and magnetic current drawn from the motor is 3 ampere. So stator copper loss is putting value it comes 41.94 watt. And now rotor copper losses considering the I1 R2M 38.16, so total core loss is 58.43, so friction voltage 19 watt. Now the input power pre output losses putting all this, so it comes to 530.53 watt. Power factor P in upon VI1, so it comes 0.8, and efficiency P out upon P in it comes 0.7, and full load torque P out is 2.4565 putting in this relation. So pull out torque is 5.1 Newton meter, and ratio pull out pull is the 5.1 2.04, which is about 200% of full load, and starting current putting this in this relation comes 14.69, which is 3 times of full load current, which is quite satisfactory. Anyhow, these are the references which we refer for developing this material. You can refer these all the books if you want to go more, and thank you very much.